so on. So you may be thinking, well, why didn't you show us this way to begin with if this is the best way? Well, it's just like whenever you first go over how to solve a quadratic equation. You're showed how to solve a quadratic equation by factoring, because in some cases that's the best way. Then you're showed how to solve a quadratic equation by completing the square. That's going all over the world to do something, but it's the process that you go through that's important. You're showed how to solve a quadratic equation then by this method that always works, the quadratic formula. Regardless of what you have, the quadratic formula is going to work. So why don't we just show students how to do that? Well, sometimes the quadratic formula is not the most efficient way to work the problem out. Just like sometimes this method is not going to be the shortest and most efficient way, but it's always going to work. Okay? Now, we have already went over variation of parameters with first degree or first order differential equations. But in order to adapt the method of variation of parameters to a second order differential equation, here's the second order differential equation. This is just the general form. So this is just a general form of a differential equation. You can have some function of x in front of the y double prime. You can have some function of x in front of the y prime. You can have some function of x in front of the y, and it's equal to some function. That's just a general form. To adapt this, our variation of parameters to a second degree, start by putting the differential equation in standard form. And so standard form is when you don't want anything in front of this y double prime, and so you divide everything by whatever this is right here, and you'd have just y double prime plus, and more than likely whenever you divide every term by this right here, that's going to change this term into something different. We're going to call that the same thing as before. That's our p of x times y prime plus the number that you get in front of the y. We're going to call that q of x y. And then of course when getting y double prime by itself, if you divide something on this side, you have to divide the other side by that. So that's going to change your g of x. We're going to then call this some f of x. Alright. Now, we have to define a few terms that we're going to use to solve these this second order differential equation by variation of parameters. We're going to use a u sub 1 and a u sub 2. And even though you don't know what a lot of this stuff that I'm about to write down is, I'm going to define it in a second. I'm going to go ahead and write down these formulas. U sub 1 prime is w sub 1 divided by w, and those w's are going to stand for something else I'm going to show you in a second. And we also have a term called u sub 2 prime, which is w sub 2 divided by w. Now, if you guessed what w stands for, then maybe you've been doing your homework from the first or second section. We went over Wronskian. Do you remember we took the Wronskian of a set of terms to tell if it was linearly dependent or independent? Okay? So that is what the w's are related to. the way that you find W sub 1, W sub 1 is always going to be equal to the 2 by 2 determinant 0 f of x y sub 2 y sub 2 prime. W sub 2 is always going to be equal to y sub 1 prime 0 f of x. So it's the 2 by 2 determinant, y sub 1 and then y sub 1 prime 0 f of x. That's the two columns. Usually when you're talking about determinants, you'll read a row and read another row, but the pattern that you follow is column down, column down. If you want to know why we have to define them like this, remember the W sub 1 and W sub 2 were solutions of the differential equation. We went over variation of parameters a long time ago. I believe when we worked it out, like you were given one solution and you had to find the other solution. If you remember, let's see, from linear algebra, I went over Cramer's rule. And whenever you're doing Cramer's rule, if you remember, it was defined with determinants. And you had this one determinant you always divided other determinants by to get solutions. And that's really, you see, this is a determinant and this is a determinant, and we're dividing by this same determinant here and here, or whatever the determinant's equal to here and here. Very similar to Cramer's rule. The regular W with no subscript is the Wronskian of the two solutions. So I have a W sub 1, I have a W. I have a W sub 2, I have a W. The W with no subscript is the Wronskian of the two functions. Remember, this is like what's happening. This is a Wronskian, it's just of a different type. But Wronskian, the Wronskian of y sub 1, y sub 2 is what this part of the formula stands for. And do you remember how to do that? Remember, the Wronskian is the 2 by 2 of 2. You have a 2 by 2 y sub 1, y sub 1 prime, y sub 2, y sub 2 prime. Okay? So, I know that I gave you these formulas first, but really, we're trying to find these u's. We're trying to find the u, and I have a u prime written down. So I have a u sub 1 prime and a u sub 2 prime. Before I can find that, I have to know what the Wronskian's equal to, and I have to know what Wronskian sub 1 and Wronskian sub 2 is equal to. That's usually what I call those, Wronskian sub 1 and Wronskian sub 2. All right. So how do we find those magical y sub 1s and y sub 2s? They will come from our auxiliary equation. So we still have an auxiliary equation. All right, here's an example of how this can all be applied. This is really the bad teacher. I say the bad teacher, but I've had teachers before that kind of skip all this and they just start working problems, and so you have no idea where any of it comes from. And then when you have to use it somewhere else, it don't make as much sense. Even if that don't make a lot of sense, it's going to help you along the way just to kind of understand what's going on there with those formulas. Okay. So instead of just jumping into the problems, I wanted to explain, you know, where all this stuff is kind of coming from. And believe me, it's okay to be a little confused now. It was confused. It's still confusing to me at times, and I've been teaching it for 10 years. So this is some pretty tough stuff at times. All right, so let's say I wanted to solve this differential equation. All right. So I could solve this by the superposition approach. I could solve this by the annihilator approach. It would take me a little while. If you get good with this approach, variation of parameters, it might be a little faster depending on how good you are with determinants. All right, so first write down the auxiliary equation and set it equal to 0. So this will be m squared minus 4m plus 4 equals 0. Will that factor? What is that? M minus 2 times m minus 2. So what are my two answers? Two. They're the same. It's a repeated answer, right? So that means that the complementary solution, that means that my complementary solution is c sub 1 e to the 2x plus c sub 2 x, that's right, e to the 2x. Remember, when you have a repeated solution, you have to put that x in there. Alright, so from your complementary solution, you get your y sub 1 and your y sub 2. Your y sub 1 is e to the 2x. Your y sub 2 is x e to the 2x. So now, we want to figure out u sub 1 prime and u sub 2 prime, because if we can figure these two out, and remember, u prime is the same thing as du, so really I'm figuring out the derivative of a u and the derivative of another u. That's all I'm figuring out. Okay, but we label it u sub 1 prime, u sub 2 prime. We want to find those so that we can solve for u sub 1 and u sub 2 by taking the integral of those, even though I haven't written anything like that up here yet. But we want to follow these formulas and do all that first. So you want to find the Wronskian of the two, then you want to find the Wronskian sub 1, and make sure for the Wronskian sub 1 that you substitute always in 0, and whatever the f of x is whatever's on the right side of our differential equation. So all of this right here, when I'm finding my Wronskian sub 1, all of that is f of x. All right, so I'm going to do all of that. I have a Wronskian to find, a Wronskian sub 1, and a Wronskian sub 2. So first I'm going to find my Wronskian. Remember, Wronskians are always square determinants. So if you have two solutions, if you have two things you're looking at, it's going to be a 2 by 2. If you have 3, it's going to be a 3 by 3, and so on and so forth. So I'm going to write that one there. Then underneath, I'm going to write the derivative. I'm going to write the next one here. And underneath, I'm going to find the derivative. First times the derivative of the second. That's going to be 2x e to the 2x. 2x plus second times derivative of the first, e to the 2x. All right. To evaluate this, remember you say this diagonal minus this diagonal. The product of this diagonal minus this diagonal. So that's going to be 2x e to the 4x plus e to the 4x. I'm saying this times both of those terms. All right, so it's that minus this product. 2x e to the 4x. So right away, you can see this term and this term are like terms. E to the 4x. All right, so we have found our Wronskian. Now we need to figure out our Wronskian sub 1 and our Wronskian sub 2. Wronskian sub 1 is going to be, you always put in the left column 0 and f of x, whatever the function is on the right side. That's x plus 1 times e to the 2x. Okay. Now this is y sub 2 and y sub 2 prime. The next column, y sub 2 is x e to the 2x. Y sub 2 prime is 2x e to the 2x plus e to the 2x. This one's a little easier to work out because that's 0 minus, now here you need to multiply that. So there's a couple ways you can do that. You could really just multiply this times this and leave it on the outside. I don't care. That would be x e to the 4x times x plus 1. It's still multiplied in. Or you can multiply the e to the 2x into both terms and then multiply each one of those times this. I don't care. This means the same thing though. Okay, so you could just leave that as negative x e to the 4x times x plus 1. It's kind of like leaving it in a little factored form there, but it means the same thing. Wronskian sub 2, remember you have y sub 1 prime, so e to the 2x, 2e to the 2x. Then you have 0 and f of x. Our f of x is the same. It's x plus 1 times e to the 2x. So find this determinant, take the product. I'm going to do the same thing I did before. I'm just going to say e to the 2x times e to the 2x and write e to the 4x and kind of leave it in this factored form. Minus 0, this product. Alright, so now we can find u sub 1 prime. U sub 1 prime is Wronskian sub 1 divided by the Wronskian. So Wronskian sub 1 prime was negative x e to the 4x times x plus 1 divided by the Wronskian up here was e to the 4x. And so usually when you do that, you're going to have some stuff cancel out. And so you see this and this cancels out. So that's going to leave me with negative x squared minus x. Now you could leave it in factored form, but I'm eventually going to have to integrate this. So I just multiplied this in here. So u sub 1 prime is equal to this. U sub 2 prime is equal to Wronskian sub 2 divided by the Wronskian. Wronskian sub 2 is e to the 4x times x plus 1. What was the Wronskian equal to? E to the 4x. So you can see these two cancel out there and just leave you with x plus 1. Now from this, I told you this is the formula for u sub 1 prime. This is the formula for u sub 2 prime. We want to get u sub 1 and u sub 2. So if you integrate this, it's going to be the integral of negative x squared minus x and the integral of x plus 1. Alright, so u sub 1 prime is going to be negative x cubed over 3 minus x squared over 2. Don't worry about the c. We got that covered. Alright, and u sub 2 is equal to x squared over 2 plus x. Alright. So I know you're thinking in your mind, where in the world am I going to get my answer from? Now, way back when we went over variation of parameters, that was a while ago, I understand. There was a way of writing the general, writing your y sub p. It was u times y sub 1 of x, or something like that. It was similar to that. Well, what we're going to do is we're gonna write it as it's u sub 1 times y sub 1 of x plus u sub 2 times y sub 2 of x. So we found u sub 1 and u sub 2. So y sub p is equal to u sub 1 is negative x cubed over 3 minus x squared over 2. That's u sub 1. Y sub 1 is e to the 2x. Plus, here's u sub 2, put in parentheses, x squared over 2 plus x. And then y sub 2, if you remember earlier, was x e to the 2x. Now, we do want to multiply all of this out in case there are some like terms or something like that. And when you multiply all of that out, you get negative x cubed over 3 e to the 2x. Then that's going to be minus x squared over 2 e to the 2x. Plus x cubed over 2 e to the 2x plus x squared e to the 2x. So, whether you see it or not, hopefully you see it, this term and this term are like terms. This term and this term are like terms. You just have to add the coefficients together. And you get that y sub p is equal to 1/6 x cubed e to the 2x plus 1/2 x squared e to the 2x. Whenever you put these two together and you put these two together, that's what you get. So we've solved for y sub c and we've solved for y sub p. So guess what? We have a general solution. And this is where we will end. I am over and I apologize. So our general solution is y equals y sub c plus y sub p equals c sub 1 e to the 2x plus c sub 2 x e to the 2x plus 1/6 x cubed e to the 2x plus 1/2 x squared e to the 2x. That's what we'll pick up on Monday.